Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. So in Module 5, we started talking about capacity management and how we can use different analytical methods to help with planning the capacity of various items in the hospital. One of those was related to the beds, and the other one was resources, and then diagnostic equipment. And I think there was one more thing I can't remember, but overall, this module wants to talk about how we can use the resources, analytical resources, to help with planning various capacities and resources that the hospital have. The ones that we started with was the bed management in the hospital. And we talked in previous session that the number of beds that are available in the healthcare settings are fixed. So they are usually not something that we can change over time, because the change in the number of beds or the change in the number of operating rooms, then the change in the number of beds in the ICUs, and all of these changes require long approval processes, because adding those extra beds or extra operating rooms can increase the cost of healthcare provided to the customers. So these hospitals can start charging the customers more just because they have expanded their capacity. However, there are rules to stop the hospitals from expanding the capacity if it's not going to be used. Because that's the only scenario under which the hospitals end up charging the customers more than what they should do. If they expand the capacity, but the capacity is not going to be used, they're going to charge the customer extra money so that they can meet at least the fixed costs associated with those capacities. So that's why there are rules. So the hospitals have to prove that if they add any extra bed, the utilizations of that extra bed would be more than 85%, then they get the approval to add that extra bed. So, however, we can use queuing theory to understand that, okay, in this system, in the current system that exists, what are the setup? What are some of the important performance measures? So let me just show it here. So let's assume this is ICU. So this is our queue. And then this is the ICU, let's assume. And these are our beds or our servers, okay? Bed 1, bed 2, bed 3. So these are 3 servers, server 1, server 2, server 3. So I consider any one of these beds as a server. So the patients come in, and these are the patients that obviously when they come in either from other floors in the hospital, when the level of intensive care, the level of when the care that is required for the patient is less intensive. So they now need to go suddenly to an ICU. Either those are the patients that come to the ICU, or these are the patients that have come from emergency department. But anyway, these patients come and they need to get access to a bed in the ICU. However, this bed may be available or not. And when they go finally to the ICU, they get the treatment, they leave. And when they leave, also, they don't get discharged from the hospital, as we saw in earlier slides. They just go to the units with that need lower intensity of care. So, and we talked in previous session that how these setups is basically similar to queuing systems. There are some beds or some servers that are available, and there are some patients that are competing for these servers. And once all the servers are full, these patients need to stay in a queue till finally they can find a bed. And also, we talked in previous session that there are different type of queuing systems, but the ones that potentially can explain the healthcare systems better are what we call as MMS. Okay, so the first one was M represents that the arrival of customers or the inter-arrival time of patients. Inter-arrival time of patients has exponential distribution. Okay, Can someone tell me what is the meaning of inter-arrival time of the patient?
It's the time between each person arriving. It's the inverse of Poisson, which is the total rate, but it's the time in between each person arriving.
It's the time between the consecutive arrival of the patient. That's what we call as inter-arrival time. So the first one, M, represents that inter-arrival time of the customers has exponential distribution. I also have this question. If you're working in a healthcare setting and you want to check this, you want to check if inter-arrival of the customers has exponential setting, how would you go about it? How would you collect data? How would you check it? Can someone else, Solomon, can you answer this question? You have had operations research, Solomon, right? Solomon?
Yeah, I'm sorry. What was that?
Um,
I answered the questions before. I'm sorry. What is your question again?
My first question is that you have had operations research, right?
I have, yes.
Okay. So my second question is that let's assume in a hospital, we want to get data and check if inter-arrival time of the customers have exponential distribution or not. How would you go about that? How would you collect data?
It's not like based on your queuing system. It depends on how many people are coming in. You just put them on a queue.
I need to collect data on inter-arrival time of the customers. Okay. Do you know what is inter-arrival time? What does it mean?
The time between each person coming in into the system.
Okay. How then would
considered your
you?
arrival time.
That's correct. How would you then go about collecting data related to this variable? Obviously, the time between arrival of consecutive customers or patients is not fixed, right? It varies.
Mm-hmm.
How would you go about collecting the data? If you were an intern, if you were an undergraduate, and this was a data that you had to collect for your project, how would you go about it?
Well, one data set would be your inter-arrival time that you just mentioned.
But how would you get inter-arrival time? So that's my question. How do you collect the data?
It would be the difference between your first patient coming in versus the second patient, and so on.
Okay, so where do you think is the best place to get this data?
As soon as they are admitted into the system at the initial start, as soon as they enter the system at the entrance is where your the first data point starts until your next patient comes in.
Okay, that's good. Yeah, that's correct. So there is an admission desk in the hospitals, and they in their database they have the time and the day of the admission of each one of the patients. So and they have also the sequence of which admission happened first and so forth. So what I would do is I would get the admission time of the patients from the hospital, and I would just calculate the difference between the admission times of consecutive customers, and these differences would give me the inter-arrival time of the customers. And then if I want to check if it has exponential distribution or not, how would you do that part, Solomon?
I think that's a tricky one. I don't recall exactly how to get that. Would that be possibly the time that when they leave the system versus when they enter?
No, I want to check. You were right about the inter-arrival time. So I want to calculate the time between arrival of consecutive customers, right? So for that, I go to the admission database. I ask for the data of the time of arrival of the customers, and then they say this is the time of the arrival of the first customer, and I have the time of arrival of the second customer and the third customers and so forth. So I have the time of arrival of the second customer minus the time of the arrival of the first customer. That gives me the first inter-arrival time that I have. That's my first data point. And then I have the arrival time of the third customer. The arrival time of the third customer, let's say that customers arrive at 10 a.m. and the second customers arrive at 10 a.m. And the first one arrived, I don't know, at 9:45. Okay, so deducting the first arrival time from the second arrival time, that shows me that the first inter-arrival time was 15 minutes, the time between arrival of 2 consecutive customers. So the first inter-arrival time is 15 minutes. That's my first data point. What is the second data point? The time between arrival of the third and the second customer. What is that data point?
10 minutes.
That's 10 minutes, okay? And I do that for all the other customers that are in the system, so they become my data points, okay? So this is the data points of inter-arrival time of the customers or the patients in this system. Now, so that is giving me the data point. But here in a queuing system, the very first thing I want to check is the distribution of the inter-arrival time. Now I have a bunch of numbers that are just inter-arrival times, but I need to know the distribution of this random variable. And obviously these numbers are all different because this inter-arrival time as our variable is random variable. It changes every time. Now I want to check if this random variable has exponential distribution or not. What would be the very first thing you would do to not only exponential for any random variable? If you have the data and you want to get a sense of the distribution of that random variable, what would be the very first thing that you would do?
You need things like
instead of doing an
average, mean, variance, and all that.
I would do something else. The average, mean, and variance cannot. Those are good, but they cannot give you. They cannot give you a sense of the distribution.
Goodness of fit test for the given distribution.
What would you do, Nathan?
Goodness of fit test for the appropriate distribution, in this case, exponential.
Okay.
And then find the sum of the residuals.
A goodness of fit test is definitely a good statistical test that you can do. But even before I get to this statistical test, what I would do is I draw a histogram, right? I'll just draw a histogram. So I'll just use Excel. I upload the data and I'll just, plot a histogram. If you have a statistical software's Minitab or anything, it would be a matter of seconds to just say, okay, this is the data, plot a histogram for me. When you plot a histogram, it gives you a bar chart of the data values. So if I see that my bar chart, for example, is something like this, what would you guess about the distribution of the data?
It's normal.
That's normal. Something around there. Obviously, I would still go ahead and do the goodness of fit test to make sure that really statistically this is correct. But just a visual quick histogram would give me a sense of the distribution of the random variable. If I have something like this, what would be your guess?
Exponential.
That's exponential. Okay, that's normal. So if I was going to do the analysis, before I do any complicated statistical test, goodness of fit and things like that, I would just do a simple histogram and I would get a sense. Because if you want to do a goodness of fit test, you will still need to know, I'm going to check if it's normal, I'm going to check if it's exponential. You still need to know this for the goodness of fit test to test, okay, is it normal? Is it exponential? Is it like multinomial, like what it is? Okay, so that's how I would do it. But let's assume we do that. We collect the data on the inter-arrival time. We do a visual test by histogram. We do a statistical test by goodness of fit, and we find out the data has exponential or any other distribution. Okay, let's assume it has exponential. And can someone tell me what is the second notation represents here? You remember, guys, from queuing theory?
That there's multiple servers, or after the queue, there's multiple people to take in the people coming from the queue.
Before we get to multiple server thing, I still need one more information so that I can do the analysis. Remember, there are two things that are critical information for any queuing system analysis. The very first time is related to how frequent your customers come to system, how fast your patients come to the hospital. That's what inter-arrival time is going to give us. What is the second one?
The exponential time in the beds in this case.
Which is our service time. So the second one is information related to service time. And here, if this is an ICU, the service time means the time that they spend in the ICU bed. That would be our service time. And M here, the notation M means service time also has exponential distribution. Now I have this question, and maybe Vicky, if maybe you can answer this question. If I want to collect data on the service time or on the time that the customers have spent on each ICU bed, how would you go about that? How would you collect that data?
I think you can pull the logs of the amount of time that they were spent in that bed from the time they were brought into the room until they left the room.
Exactly, yeah. So I would again go get the permission of the hospital. So I can have access to the database of the hospital in which they hold the information of the patient. And for each one of the patients, I look at the time that they got admitted to the ICU until the time that they left the ICU. And that would be the occupation time or the service time associated with each one of those beds, which I treat each one of those beds as a server, right? And then if I want to check if it has exponential distribution or not, I will do the same. First, I visually check it with a histogram, and then I will do more sophisticated tests with goodness of the fit test or other tests that exist. And then what is the third notation? What does this one show? Diana? Diana, are you here?
Sorry, what did he say? I'm sorry.
Can you tell me what does S show? In the queuing system notation, what does S mean?
Or
I couldn't hear you clearly. Can you repeat one more time?
yeah, the number of beds or how many servers you have.
Exactly, number of servers. And there are actually a couple of other notations that we usually put for queuing systems, but these three, I would say, are the most important one. How the customers, the frequency of the arrival of the customers to the system, the frequency by which the patients or customers get the service and leave the system, and how many servers we have. Okay. And in the video that I showed, that I posted for you guys, there was one related to MMS systems as well, right? Am I correct? Did you guys watch that video? Yeah. So there was also a video related to MMS systems, and when I explain how to use the formula and how to calculate various things related to a queuing system. So in any queuing system, and before I proceed, let me just make sure. In this class, everyone has had operations research except Vicky. Am I correct? Vicky, you did not have operations research, right?
No, I didn't.
But everyone else has, I believe. Let me then go ahead. So in any queuing system, as I said, we have a queue, and then we have some servers. Okay. Bed 1 or server 1, bed 2, bed 3, bed 4, as many servers as you want to have. Patients come in, and then they leave the system. So there are a couple of important performance measures for this queuing system. Let's assume this is an ICU, or let's assume this is the floor of a hospital. What would be some of those important performance measures that you want to measure for any queuing system?
Maybe average time spent in the queue or boarding, if that's our queue.
Okay, so WQ, average time waiting in queue. And similar, related to WQ, another metric that I would want to know is LQ. That's number of people, number of patients, number of customers waiting in the queue. Okay, those are two. What else?
Like block time.
Those are important too, but let's say all of those in this they are in this waiting. Let's say if I know the waiting time, I'll know how much of it was block time and how much of it was just waiting. But let's consider all of them as, because block time, let me just say, for those of you who may not remember, we had that in the simulation. Block time is when you are in the queue, but you are the first person in the queue. But when I say waiting time, it's just the waiting in the queue, no matter if you're the first person or the 10th person. Let's assume the WQ takes care of all of them. If you remember from queuing theory, we also need to know W and L. What is W? What is the difference between W and WQ?
WQ is time waiting in the queue.
And W is?
Just time waiting in the system.
Average time waiting in the system. And what do you mean by system?
The time that you enter into a queuing until you disbound.
Exactly. So when I say system, I mean the whole thing. Queue and the server. When I say WQ, it's just the time waiting in the queue till they finally go to get a bed. But when I say the time in the system, it's from the time that they enter a queue till the time that they leave. They are done with the ICU bed, they leave the ICU. That's the time waiting in the system. And obviously L then would be number of customers or number of patients waiting in the system. And that means number of patients that not only those that are in the queue waiting, but also the ones that are in the ICU getting the service. Number of patients in the system. And we can also look at WS and LS. Do you remember what are those?
Time spent in the service area.
WS would be average time.
Average time spent in the service area, and the same for L, number of people.
Exactly. In the service area, which is in the ICU, for example, and LS would be average number of patients in the service area. And WS, which is average time spent in the system area, we already know is 1 over mu. Mu is the service rate, and we know the average of the service rate is the time you spend in the service area. Okay. And do you agree that I can say that W equals to WQ plus WS? And do you agree that L equals to LQ plus LS? Do they make sense? What do they mean? What does this one mean? The first one. Anyone?
Yeah, isn't that your average time overall? It's adding your queue time plus your time at the service area.
Exactly.
And that gives you, yeah.
Exactly. So the time for waiting in the system is the time in the queue plus the time in the service area. And also the total number of people in the system is number of people in the queue plus number of people in the service area. Okay. And to be able to calculate all of these important performance measures related to a queuing system, I need to know one thing. Any guess? Do you remember what was pi j? I have to go ask Dr. Safe to give you guys a net for the queuing system. For any queuing system, what those pi ratios? Those are steady state
Probabilities.
probabilities. What do they mean?
It's when the queue and working system has been operating long enough that it's at a steady state, meaning it's not at the very beginning or close to termination, if that exists. It's been in processing for a while.
Okay, so these are the things that we measure in the steady state. When the system has been running long enough, the system has reached equilibrium. What do they measure? The probability of?
Are you looking for that they're discrete, meaning each one's like the probability of 1, 2, 3? Is that what you're looking for?
Yeah, so pi j or pi 5, what does that mean? What does it represent? So if I say, so that's a probability, for example, so that's for sure something between 0 and 1. If I say pi j is 0.9, what does that mean?
It means of that exact situation. So of
What is that situation? That's what I want to know. What is that situation?
I forget exactly. I think isn't pi just that number of people in the system?
Probability
At
of
least that many?
having, yeah, probability of having j number of people in the system. That's exactly what it means.
Sorry, yeah, I've seen rho and pi. I was getting mixed up in my head. Sorry about that.
No worries, no worries. Yeah, so pi j's steady state probabilities means that what is the chance that if I let the system work, let the patients come in, get the service, leave, at some point stop the system and look at the number of patients in the system, either the ones that are waiting to get to ICU or the ones that already have an ICU beds. What is the probability that you see 10 patients in the system? What is the probability that you see 20 patients in the system? Okay, so that would be pi j, the probability of having j number of people in the system. So what does pi s means here in this system? Remember, in our system is m s, and let's assume this is an ICU, and s we said is number of servers or number of beds in the ICU. What does pi s measures? Probability of having S number of patients in the system. Okay, so if let's assume, okay, this is Q and this is ICU. Let's assume I have 5, if I can put 5 beds here. Let's assume one of them is here. Okay, so this is an M5. 5 servers, 5 beds. That 1, 2, 3, 4, 5. And in this system, I'm analyzing this system and I calculate pi 5. What does pi 5 mean? What does it represent? Probability of having 5 patients in the system. Can you rephrase this in a different way? Like if I have 5 patients in this system, and remember, this is my system. I have 5 patients in this system. Where do those patients go?
Directly with the servers or in the beds?
Exactly. If you have 5 patients in this system, they're obviously, and there are 5 beds here, so they just go occupy the beds. They don't wait in the line, because if you have 4 patients in the system in the ICU, for sure then one of the beds are idle. So when a new patient comes, when the 5th patient comes, the 5th patient also gets this bed. Okay, so if you have 5 people in the 5 patients in the system, then those 5 patients are not going to just wait in the line for no reason. They just go to the ICU and occupy the beds. And when this happens, then ICU is full. Okay, when this happens, then a new patient What happens to a new patient? Let's assume a 6th patient arrived. 6th patient. What is going to happen to the 6th patient?
Has to wait in the queue.
Has to wait in the queue. So then I can also say that pi 5 is the probability that there are 5 patients in the system. We can calculate pi 0, meaning that probability that there is no one in the system. Pi 1, there is 1 patient in the system, 2 patients in the system, 3, go all the way to pi s, which means there are s people in the system, which means the ICU is full, assuming the ICU has s beds, and then we can go all the way to pi s plus 1. There are s plus 1 patients in the system, ICU is full and 1 person is waiting, pi s plus 2, and go all the way to infinity, assuming there's no limit on how many customers can wait or how many patients can wait in the system. Right? So as I said, to be able to calculate L, LQ, W, WQ, and all of those, I need to know these probabilities. So what is the formula that you can use to calculate these probabilities? This is the formula for pi 0. So that's the formula that we can use for for pi 0. And here rho is lambda over S mu. Mu is the rate of service, or the rate of, which is 1 over service time. And then lambda is the rate of arrival, which is 1 over inter-arrival time. And S is number of servers. So with that, you have everything in this formula. You can calculate pi 0, and then pi j for j from 1 all the way to s. If you want to calculate pi 1, pi 2, all the way to pi s, the formula for pi j would be s rho to the power of j, pi 0, the pi 0 that you calculate from the formula above, over j factorial, and then pi j for j anywhere from s plus 1 all the way to infinity would be s rho j, pi 0, s factorial, and s j minus s. Okay. And so that helps you to calculate pi j for any value of j. If you want to calculate pi j, the probability that there are j patients in the system, for j from 1 to s, you use this formula. If you want to calculate the probability that there are j patients in the system for j equals to s plus 1, s plus 2, and higher values, you calculate the second formula. And then there is also a probability that I calculate here, probability of j greater than or equal to s, and the formula is s rho to the power of s pi 0. That pi 0 is extremely important. You can calculate that. You can calculate anything else. 1 minus rho. Can you tell me in words, what does this probability calculate? Probability of, and j is actually number of people in the system. So as I said, pi j means probability of j people in the system. So j means number of people in the system. So probability of j greater than or equal to s, what does that mean? In words. You're looking at an MMS system, an ICU that has S number of beds.
It's full.
Exactly. That's probability that ICU is full. So if I ask you, what is the probability that the ICU is full? this is what you need to calculate. So for the MMM5 examples that we calculated, we can have to calculate the probability of J, number of people in the system greater than or equal to 5. If you calculate probability of J equals to 5, that's probability of having 5 people in the system. Obviously, in this scenario, also ICU is full, but that's not the only scenario. If when you have 6 number of people in the system as well, still the ICU is full. 5 of them are occupying the bed and 1 of them is waiting. Still the ICU is full. When you have 7 people in the system, still the ICU is full. 8 people in the system, still the ICU is full. That's why the probability of ICU being full is the probability that number of people in the system being greater than or equal to 5. Equal to 5 or greater than 5. That's the probability that the ICU is full. So if I ask you what is the chance that the ICU is full or the floor is full or the emergency department is full, this is what you need to calculate. Okay. And then finally, after all these calculations, we need, this is the formula for those important performance metrics that we actually needed in the first place. LQ is probability of J greater than or equal to S rho 1 minus rho, and then WQ is always LQ, whatever you calculate in LQ over lambda, and WS, the time they spend in the service area, is 1 over mu, and then LS is lambda over mu, and we just said on the top that L equals to LQ plus LS, W equals to WQ plus WS. So just add LQ and LS to get L, and add WQ and WS to get W. Okay. So those are the important performance metrics for a queuing system. So when you have an ICU, you want to know what is the probability that the ICU is full, okay? And you want this probability to be high or low? Do you want the probability that the ICU is full to be high or low?
Low, so no one's waiting.
We want that to be low, but not, but there are some specific thresholds that I'll talk about in a little bit. But yeah, so for some of those, so we calculate some of these probabilities because those are the performance metrics that can show us how the system is performing. If I calculate probability that the ICU is full and it's 95%, then that's definitely something that is going wrong, because 95% of the times ICU is full. So 95% of the time, then the patient needs to get to a high ICU bed, they cannot, and they have to wait. That means definitely this hospital has to expand the capacity. And these are the type of metrics and these are the type of numbers that we can bring to the board of decision makers to show that we do need to expand the capacity of the ICU of the hospitals or the floor and so forth. Okay. So those are the ones that we need to calculate and talk about. In healthcare facilities, as I said, we usually have fixed capacity, fixed number of beds, fixed number of operating rooms, fixed number of diagnostic machines and imaging machines and so forth. For some of these fixed resources, let's say MRI machines, MRI machines or X-rays, you always have to set an appointment. So you cannot just walk in and say, okay, I just walked in, can I do an MRI? That's not going to ever happen. You always have to set an appointment. And for those fixed resources like MRI machines or imaging resources, where the operations is done by appointments, the chance of congestions and the chance of patients waiting is really, really low, unless the scheduling is really bad, unless the appointment time is really bad. So, for example, the patients get their appointment, but they don't arrive on time. Obviously, they end up waiting because other patients have arrived, they have to go through MRI, so maybe you just push them to the end of the line. Yeah, they end up waiting. But if you arrive on time at the time of your schedule, usually the waiting time is really short. Okay, so for those resources, when we consider the fixed time slots for the operations to be done on the patients, like MRI appointments, there's basically no need to queuing theory. It's just appointments. As long as you know how long each patient needs, how long MRI of each patient takes, and how many patients are coming. Let's say it takes an hour for each MRI of each patient. Okay, so you give time to each patient every 1 hour, and when they arrive, if they arrive on time, they get their service and they leave, and everything is fine. In those scenarios, for these fixed time slots, we don't need queuing theory. We need queuing theory for the scenarios when the arrival of the patients is random, like ICU beds or the floor beds, and these are the scenarios when, or emergency departments, arrival of the patients are random. It goes up and down in different times of the day, in different days of the week. And for those scenarios, we need to use queuing systems to have a better sense of how the setups of these queuing systems, or the ICU or the floor or the emergency department is working. And for the MMS system, let's assume, and we had that shortly in the video. If we know the arrival rate as 14.8 patients per day arrive to this hospital X, so this is obstetrics units. Obstetrics units are the ones in charge of pregnancy and delivery of babies. And the reason that this example is given, because those obstetrics units usually are independent from the rest of the hospitals, and they work on their own. So here, the capacity or the resource that we are talking about is number of postpartum care beds. So those are number of beds when they give birth, and they need to stay on the bed a little more for all after delivery treatments, if anything is needed. So the number of patients that arrive per day to this hospital for the care, for the delivery, and so forth is 14.8 on average. And the time that they spend on each one of these beds is 2.9 days. So that's the time they spend, that's the service time. So that's 1/mu, which is service rate, okay? And here we have 56 beds. We talked in previous session that we can use in this MMS formula or queuing system as a descriptive or prescriptive tool. So as a descriptive tool, we can use the formulas that we just showed to show that what is the probability of a delayed admission, okay? What is the probability that the patient that gets to the system gets delayed, they need to wait. And we just showed that would be the probability of J greater than or equal to S. Because if the number of patients in a ICU or in a healthcare setting is S, which means the number of beds that are available, or anything greater than S, then that's when a new patient has to wait. So probability of delayed admission, the probability that a patient has to wait, is probability of J greater than or equal to S, that we just learned how to calculate. And for these with these numbers, that probability would be 4%. So for this hospital, the probability that a new pregnant woman who is about to deliver has to wait and cannot find a bed right away is only 4%, which is reasonably low, but it's still not as low as it should be. And if I want to use this MMS system as a prescriptive tool, as a tool that I can use maybe for optimization, close to optimization, that would be this example where I need to know that by changing the number of beds, obviously, how the probability of delay would change. Obviously, as I change the number of beds in this hospital, if I increase number of beds, how do you expect the probability of delay would change? If you increase number of beds in this hospital, and I'm looking at probability that the new patient has to wait to get a bed, you are increasing number of beds. How do you think that probability would change? Is it going to go up or down?
If there's more beds, there should be less of a probability.
Exactly. As you increase number of beds, going from 56 to 58 to 60, the probability that the new patient has to wait is going to go down from almost 4% with 56 beds that we have right now. We go to almost 1%. If we go to 60, we almost go to 1%. The chance that the new patient has to wait and everything is. And obviously, if I reduce number of beds, the probability that the patient has to wait is going to increase. Okay. So the reason that we said we are going to use this as a prescriptive tool is that it prescribes for you that if you want to have only 1% chance of a patient waiting, I'm going to prescribe for you to use 60 beds in this hospital. That's why it's called prescriptive way of using queuing system. And those numbers are important because there are actually rules. I forgot the name of the union, but there are rules that when you develop a hospital, you have to think of number of beds that are needed such that the probability of delay for a new patient should not exceed 1%. And if that's the condition I have to have, and as I design how many beds I need in my healthcare setting, then I have to find number of beds such that the probability of delay, the probability that the new patient is going to wait is definitely less than 1%. So in that scenario, I would recommend 60 number of beds. And with 60 number of beds, and with that arrival and of the customer and service rate of the customer, the utilization or occupancy levels is about 70%, 71%. So about 70% of the beds are utilized. So or each one of the beds is utilized 70% of the time. Okay, and also that's important because there is also another American College of Obstetrics and Gynecology recommendation that the beds should have less than 75% utilization. If your beds are utilized more than 75%, then that's too much. So you have to think about increasing the number of beds. So with the 1% thing, at least in this setup, the utilization of the beds is 71%, which is also less than this 75% rule that exists. So if you guys are ever in charge of doing these calculations, doing these calculations for emergency room, for a hospital, for a floor, for a bed, for a ICU, make sure to also ask for these numbers. Obviously, you can go ahead and with finding out the parameters of a queuing system, you can find out that what is the probability of wait or probability of delay with the current number of beds? How about what if you increase number of beds? What if you decrease number of beds? How the probability of delay or how the probability that the patient has to wait would change, would decrease or increase? But then once you know these numbers, you can also ask from the hospital, is there any regulations that we have to meet? If they provide you with those regulations, 1%, 2%, 3%, then they make sure you take those into consideration as you are recommending number of beds that this hospital needs to have. Okay. And all these numbers can be calculated by the formula that I just showed you guys. And the easiest way always for this type of system is to, I do the calculations in Excel file. I'll just open an Excel file, write the formula in Excel, and just copy the formula, and I calculate pi j for any value of j I need and so forth. So that's always the easiest way to do for me. And there are also some software for queuing models. One of them is Q Tickets, Q Miners, QSP. I haven't used them, and you can. And there are also some other optimization softwares in which you may be able to find. They may be able to do calculations related to queuing theory as well, but I always have used Excel. I just write the formula in Excel and then I'll just do the calculations easily for any value of pi j, pi 1, pi 2, pi 10, anything. Okay, as we are talking about queuing systems in healthcare, I need you guys to also be cautious about a couple of things. The formula that we just talked about, in that formula, there is a priority rule. The rule that we already, that by default is in all these queuing models that we use, is first come, first serve, which means for those patients that are waiting in the line to finally get admitted to the hospital or to an ICU bed, the first person in the line is the first person who is going to be served. However, we know that's not always the case. For example, emergency room is a good example. We may have some patients that are being treated, or some patients that have occupied a bed already. But if we get some patients that are really, really in super urgent situations, then we may stop the treatment of that patient, of the previous patient, and start working on the super urgent patient. So in those are the scenarios where we call preemptive, which means if a high priority customer, if a high priority patient arrives, we stop the working, or we stop treating the lower priority patients. We work on the high priority patients, and then we go back again and resume the treatment of the low priority patients. That's what we call the priority rule is called preemptive. And non-preemptive are the ones in which we don't do these things. So, and sometimes in our systems, like an emergency department, we have a combination of preemptive and non-preemptive systems. For example, in a hospital emergency department, the very first time that they see a patient, the triage part, when they want to see what is going on with each patient, what type of treatments they need, how severe their situation is, that's usually a non-preemptive. No matter if you have a bad situation or not super urgent, you wait in the line. They are going to look at you. They are going to identify what you need and how severe your situation is. Usually in emergency department, the first time the patient sees a nurse is a non-preemptive. Just a wait in the line, first come, first serve. But when they go to an actual doctor for the treatment, that's when it's preemptive. If we suddenly get a stroke patient, an accident patient, and that patient needs to go to a doctor right away, then we stop providing service to the patient that has lower emergency level, and we treat the patient with a higher emergency level, and then we go back with resume the service to the lower priority level. And obviously with any one of these, with changing the priority rules and everything, the formulas would change and the system becomes more complex mathematically, like queuing theory. Can someone tell me that as the system becomes more and more complex, what other tool I can use other than queuing system?
Simulation?
Simulation, exactly. The base of the simulation, the logic behind the simulation, all of it is queuing theory, all of it. Because remember, in simulation, every model that we developed was a queuing system. The parts came, they waited in the queue, they waited to get processed. The customers came to a bank or to a call center, they waited in the queue till they finally get processed. Every model we developed in simulation was a queuing system. However, the main difference between the simulation and queuing system is that in queuing theory, because it's mathematical, there is some limitation on how complex this queuing system can get, but in the simulation, there's no limit on the level of complexity of the queuing system. Your queuing system can be as complex as you want. Still, the simulation can manage it. But in queuing theory, there is because it's a mathematical model, there's a limit on the level of complexity that you can capture. However, the numbers that you get from queuing theory, L, LQ, all those probabilities that you get from queuing theory, they're all exact numbers. That's mathematical formula. Those are exact numbers. But the numbers that you get from simulation, those are all approximations, estimations, because because simulation behind the scenes is a numerical model. It doesn't use any formula. It just as if it's real work. The patient comes in, the patient goes through the ICU and leaves. So the system records how long the patient has stayed in the ICU. Okay, that's the number. And then the second patient comes and the third patient comes. For all of them behind the scene, the simulation software records how long they waited in ICU. And at the end reports the average of these numbers. If you run your system longer, this average is going to change a little bit, not much, but a little bit. So the numbers that we get from the simulation are approximations. They're close to the exact numbers, but they're approximations. So that's disadvantage of the simulation. However, there is no limit on complexity of the system that you can capture. When we come to queuing theory, on the other hand, it's a mathematical model. You saw it, all mathematical formulations. The numbers that you get are exact numbers. However, there is a limit on the complexity of these systems that you can capture. So each one of them has advantage, disadvantage. Time, okay, we still have a couple of minutes. Yes, so MMS is really a good queuing system to represent what is happening in a healthcare setting. However, there are other type of queuing systems that you have learned in your queuing system class. Here, I'm just going to go over them quickly. And Vicky, when you get to the operations research class, you learn more about these parts. So the reason I'm not going into the detail of these tools, obviously, is because this class is not the class to go into the detail of a tool and teach a tool. You're supposed to know it and then just learn about the application in queuing in healthcare theory. As I go through each tool, I just talk a little bit more about each one of them to refresh your mind, but the details and everything are the ones that you already have learned in operations research or you're going to learn. But anyway, another type of queuing system is an MMSK. And this notation, the fourth notation in a queuing system, shows the capacity of a system. In all the examples I gave you, when I said MMS, I assume this fourth notation is infinity, which means the capacity of the system is infinity. There is no limit on how many patients can be in the system. The ICU may be full, but if you even want infinite number of patients can wait in the waiting room. Okay, that was the assumption. However, that might not be very realistic. K shows the capacity of the system. How many patients can be in the system? And when I say system, I mean ICU and the waiting area. If you have only space for 5 patients to wait in the waiting area and 10 patients to be in the ICU, then your K, which is capacity of the system, is 15. Overall, 15 patients can be in your system, 10 in ICU, 5 in the waiting area. If a new patient comes in and this system is full, all 15 patients are there, the patient has to leave, goes to another hospital and so forth. Okay. So those are also fine. That's what we call is that finite capacity. The capacity of the system, the number of patients that can be in the system is finite, is limited. Finite capacity models. And the formulas are the ones that you already have learned in queuing system. And when K equals to S, which means no patient can wait. If number of patients in the ICU is full, then that's it. K equals to S means the capacity of the system equals to number of beds in the system. If the hospital has 10 beds, that's it. The capacity of the system is also 10. No patient can wait for the hospital beds. And those are the systems that we call pure loss models, meaning that 11th patient that comes is a loss, that the patient has to leave the system if we cannot treat that patient. So when K equals to S, that means the capacity of the system equals to the number of servers in the system. So there is no room for a waiting area for a queue. And then the other type of queuing systems that you may use to treat a healthcare setting is MG1 and GGS. Can you tell me when I put G instead of M, what does that mean? Instead of MMS, I put GGS. What does that mean? That means the time of the service, the inter-arrival time of the patients or the service time of the patients have general distributions. Any distribution. It's not exponential, it's general, normal, I don't know, variable, any distribution. So GGS means the interarrival time and the service time have general distributions, and the number of servers or the number of beds in the system is S. And MG1, interarrival time is exponential, the service time is general, and there's only one server in the system. This may be a good one for maybe operating room if you have one, or diagnostic machines and so forth. In the hospitals, we have higher utilization of the beds than what we want. As we said in a couple of previous slides, there are rules or there are regulations that we do not want the occupancy of the hospital or some of these beds to be more than 75% level, or 85% for some scenarios. So maybe for the pregnancy units is 75%. For some other units, it's up to 85% as well. But we don't want the utilization of the beds of those units to be, let's say, greater than 85%. However, most of the time, we end up with scenarios where the utilization is actually a little higher. And those are the scenarios where the number of patients that come to the system varies. However, we can predict when it's going to be higher. So the change in the demand is predictable. We know overall we get on average maybe 10 patients a day, but we know that on Saturday and Sunday, it goes to 15 patients a day. We know that maybe at some hours of the day, the number goes higher. So through some historical data, we know when that the arrival of the patients is going to change, it's going to go higher or lower, which time of the day, which day of the week. So those ups and downs are predictable. If that's the case, then for those moments, for those specific hours, for those days, we can keep some extra beds that we can use later in those scenarios. Or there is other term, they call it swing beds. So if we have, let's say, a unit that is in charge of providing service to pregnant women. And for pregnancy, the historical data has shown that actually January or winter is the lowest time. It's the time that the rate of people who come to give birth is low, and then July and summer is high. So I know then for this unit, then probably in the summer, I need more beds because I expect more people to come. So those are predictable surges in the demand. So, however, let's assume I have another unit in which the demand is going to go high in winter and is going to be low in summer. If that's the case, then I can have some beds that use some extra beds that use in that unit in winter, since the demand is high. However, in summer, when the demand in the pregnancy department is going to go up, these beds are going to go to the unit that provides service to the pregnant woman. So that's what we call swing beds. If you have some units and they go up and down at different parts of the year, we can have some beds that swing between these departments. So in that scenario, we can meet the demand of these demand associated with these predictable changes. Okay. So that's what I wanted to cover for the queuing system related to estimation of or evaluating the situation of a system mid-queuing theory. Finding the probability that a patient has to wait, the probability that the system is full, knowing the average number of patients that are in the system or in the queue, how long they are going to spend time in the system or how long they're going to spend time in the queue. So we can use queuing theory to calculate these measures for our system, for our queuing systems, an ICU, emergency department, a floor. And these are the numbers that we can always take to a board if we want to argue why we have to expand the capacity of the unit or why we have to actually decrease the capacity of the unit. Maybe we have so many beds that are not going to be used for you. Still, you can use queuing theory to show that this is the utilization of the bed, or this is the percentage of the time that the bed is idle. So if it saves money, just use that bed and use it in a different part of the healthcare setting. The rest are related to staffing levels. So what we covered in this session and toward the end of previous session was how to use queuing theory for managing number of beds. But next session we will talk about managing the staff level.